Another way to use proportions is with similar triangles. Two triangles are considered similar if they have the same angles and their side lengths are proportional. If we have two similar triangles, we can solve for their unknown side length by creating ratios and solving proportions. And in order for us to use a proportion, we need to know that the triangles are similar. And in this case, you're going to be told the triangles are similar. These are similar triangles. And the first thing you might want to do is pull out your ratios. So create ratios. And then from there, we can create our proportion and solve it. So in this case, for number one, we're given visually two triangles that are similar, and we want to find the unknown side here, which is x. Well, in order to do that, I need to know which sides are proportional to that side. I need to know which sides are essentially the same for the triangle. So it's helpful to kind of visualize, kind of thinking about where that triangle might sit if I were to actually move that triangle to be over here. If it was sitting on top of it like that, where would these sides be? It's hard to move it without changing the sides, but so we have, this is the 10, and I'm going to do different marks here so that we know which sides are which. So the 10, the 24, and the 26. So now I'm going to move that. And we're not going to care that the triangle size is moving. We're just moving it here so we can compare which side of our small triangle matches with the larger triangle. Now, you may want to do this visually in your head, but if you can't, you can always use a sheet of paper and kind of move the paper around on top of the triangles to do that. But when we do this, we can see that this blue side matches up with our unknown, and the blue side is 10. So that tells me that these two are our first ratio. So we have that x to 10 is our first ratio. Now, our second ratio can be any of the sides. It doesn't matter whether it's this side or this side or this side. It doesn't matter. I tend to choose the side the triangle sits on if possible, just because for me, finding the side the triangle sits on and its matching side of this other triangle, visually, I can see it a little bit better, but it's up to you which side you want to find. But I'm going to look for this side, which is the orange side, it looks like. So my second ratio is 45.6 to 24. And now we have two ratios. And now that I have two ratios, I can write my proportions. And as I mentioned in the first video, you can write your proportions where you pair up your things like this, or you can pair them up like this. I'm going to use large triangle compared to small triangle rather than side compared to side. So I will have x over 10 equals 45.6 over 24. So I'm doing, actually this is side compared to side, because we have blue, blue. These are sides and these are sides. They're already written as ratios. And so I'm just using the ratios that I already wrote to make my proportion, essentially. And now I can cross multiply. Not doing a very good job of making straight lines here. Um, 45.6 times 10 is just going to move that decimal place over to give us 456. And then I will divide everything by 24. It's not enough room to write. But 456 divided by 24 is going to be 19 feet. So the unknown side is 19 feet. In some cases, you will have a word problem that doesn't have the triangle drawn for you. And so you will have to draw the triangle yourself and then piece together all of the information. This question says, if a 15-meter flagpole casts a shadow that is 33 meters long, how long is the shadow cast by a tree? So we're looking at a flagpole. There's a flagpole. And the flagpole is 15 meters. And it casts a shadow that is 30 meters. There's our triangle. And we're looking at how long the shadow will be for a tree. And the tree is 24 meters. We don't know how long the shadow is going to be. And these are proportional because they're perpendicular to the ground, and if it's happening at the exact same time of day, the angle of the sun will be the same, which makes these angles the same, giving us similar triangles. So I'm going to move that here, make this a little smaller. And these are meters. So I'll put my unit there. And instead of question mark, I should probably put a variable. I would put S for shadow, but S's look like, the letter 5 sometimes. So we'll put X. And my ratio, I only have 4 sets of numbers, and so I don't really need to write out the ratio like this unless you really want to. But I'll just compare side, because those are obviously the same on the same sides because they're both on the ground, and side, because those are the ones sticking up out of the ground. They're the trees. So we'll have 30 to X equals 1224. And now we can cross multiply. 15x equals, and then we'll have 24 times 30, which is 720. And so our shadow, when we divide 720 by 15, is going to be 48 meters. And that makes sense because the tree is taller, which means our shadow should be longer than the shadow of the flagpole. We're going to look at one more. This example has the triangles kind of what we call inscribed. They're once inside of the other, but we still have two triangles. And when the triangles are one inside of the other, that's another way that we can tell that they are similar, because once again, like the flagpole one, they both have 90-degree angles. The angle of the sun's going to be the same, and so they have the same angles here. So the two of the angles are the same, which means all three of the angles are going to be the same, making them similar triangles. So it says, suppose you are standing such that a 45-foot tree is directly between you and the sun. So you're here and Mr. Sunshine is up here. That was my attempt to make sun rays, but it looks like a flower. So we'll do the old school one. If you are standing 120 feet away from the tree, this is you standing from the tree, and the tree casts a 135-foot shadow, how tall could you be and still be completely in the shade of the tree? So this one is a little tricky because we've got to think about a few different things. First of all, we have some information about this bigger triangle. Let's redraw that bigger triangle here so that we kind of look at just that triangle for the tree. We know the tree is 45 feet tall and it has a shadow of 135 feet. And now we also need to know some information about this smaller triangle. And if you look at that smaller triangle, I don't see any actual numbers for just that smaller triangle. We're trying to figure out how tall we should be to make sure that we are in that space, but I don't see any number for my shadow. However, I can find a number for my shadow because if we look at the tree's shadow, we know that from where the shadow ends to where the tree begins is 135 feet. And we are 120 feet from the tree, which means if we want our shadow to end where the tree shadow ends, we want to make up the difference between the 120 and the 135. So if I do 135 minus 120, this is the length of what our shadow should be. And now that we know how long our shadow should be, we actually have enough information because now we have two ratios. We have two numbers for the bottom of our triangles, and we have one number for the sides so that we can find the other side. So now I can create my proportion and solve it. $15 times 45 is 675. And 675 divided by 135 is 5. I need to be 5 feet tall, which I am not. I am taller than that, which means my shadow is going to be over here, going much further than the shadow of the tree. But that is using proportions for triangles.